Is that a problem? Like
for the tapping in? I think that's fine. Yeah, nothing you could do now.
Yeah, no, like I was wondering if attendance were like monitored by them.
I'm not sure, but we don't use that in the grading, so it's not going to be. Okay, so let's wait another minute because some of you may have other lectures and stuff to attend. So let's just give another minute for them to arrive and then we'll start. Okay, let's start. So, a few quick announcements. Before we start. Okay, a few quick announcements before we start. We have the last lab session on Tuesday, okay? And for that lab session, you will need the data from the previous lab session, which was in week 8. So please make sure you bring that snapshot or whatever form of recording that you have, and then we'll give you a new piece of paper. I guess a lot of you have left a piece of paper behind and it's been a while, so we'll print a new piece of paper. Just make sure to input the values you got the last time, add the new ones, and then take another snapshot of that, or basically an image of that to use that for your analysis. Now, I'll talk a little bit more about what we're going to do in the lab towards the last 5 minutes of this session, but just make sure that you're all there. You've already done a big chunk of it, which was printing the structures, and now you're just using the chips to actually do some analysis. So the good thing is you've got all the printing done, and now you're going to do mass measurement and the diffusion test. The second announcement is regarding next week, Thursday's lecture. We won't have a lecture, as you know, we'll have the exam in the class time, so it will be from noon to 1 p.m. The details of the assessment are on the assessment tab in QM+, but it's going to be in that 1 hour slot, and you're only going to have half an hour to respond to that. So as soon as you start the attempt, there's a limited 30-minute window to finish your attempt, and you're only allowed to have one attempt. It will only include lab 2 and 3 content, but it can be any sort of concepts you've learned in the class, or data that you've recorded, or stuff in the slides, anything, but only limited to the hands-on stuff that you've done in class in those 2 labs. So that's that, and then the last thing is we have, this is our last lecture. I may upload one more video for you guys to view under either this week or the week before, but basically that's going to be the last piece of recording. So that will probably be a little bit more about neuroprosthetics and materials there, because we really don't have time to cover it here in this lecture. But don't worry about that. It won't be included in the exam. If you're interested in learning more about that area, you can watch that video, but it's not going to be included in the exam. yeah, basically that's it. And the Tuesday labs, you may have been shuffled in terms of your hours, but we're going to make sure that you get your own samples when you enter the lab. So we've sort of made arrangements so that you get into the same grouping that you started the lab sessions with. So that's that, and not much really to cover apart from that. There's going to be approximately 10 questions in the quiz, and it's going to be very easy to answer if you've done the work in the lab. So I'll look forward to seeing you there on Tuesday. Okay? This week, and in this in-person lecture, we're going to talk a little bit about the completion of this excretory system lecture set, which is we haven't discussed the mechanics of the excretory system, and we're also going to talk a little bit about natural polymers and natural proteins, and how we actually implement them in engineering the tissues associated with this system. I've uploaded the slides for this, so if you need to take notes, thank you for that comment 3 weeks ago. So since then I've tried to keep them all uploaded before the lecture, but pretty much everything is included here. If you have notes, it's good to have those on extra additional stuff. So today, again, we're going to start talking about natural materials. This is something we've talked about probably the least amongst all these different sections. And in all of these tissues, you have a variety of material physics or material types. Proteins are a big, very huge class of materials that your body is actually constructed with. Polysaccharides and sugars are the next big class, and then you've got minerals. But today we're actually interested in looking at proteins, okay? And proteins exist everywhere. We're going to put our focus on collagen and a little bit of elastin and gelatin, but collagen is 30% of the entire pool of all the proteins in your body, and it's not just one type. You have about 30 types of collagen. It's not just in the skin, where you're most familiar with. It's in the epithelial layers of the lung alveoli. It's all the way in the linings of your internal organs, as well as your, of course, skin, the ligament and cartilage. It's everywhere, okay? It's a connective protein that is present in pretty much any form of connective tissue, and we'll look at its structure and function in detail today, because it's a big chunk of what today shapes our library of biomaterials when we think about tissue engineering. So that's why we've sort of picked that as our focus today. So proteins are polyamerides, and you may or may not be familiar with that terminology. It's that NH2 group that links with the OH group, hydroxyl group, or carboxyl group on the other end, and it forms a chain reaction that produces the overall protein backbone, very much like polymerization in any other monomer. And so that's the building unit of those, and of course you're familiar with different types of amino acids involved. The interesting thing is that the side groups, which are those large chunky electrostatic fields that form the geometry of the protein backbone, play the most important role in defining the function of the overall protein. And so that's why if you study the chemistry of these individual sequences in a protein structure, you'll see that those electrostatic interactions are what define the macroscopic structures, such as the helical bends, and that sort of translates into the fiber structure and then the overall tissue. So collagen usually has one of these two sequences, and depending on which of these it has and in which sequence then these two come next to each other, it determines different versions of collagen. And the way we detect whether or not we've been able to synthesize collagen is we look at hydroxyproline, which is one that uniquely occurs in collagen, and so that tells us the purity of collagen in the sample that we generate in the lab. And as I mentioned, it consumes 30%, that's why we're specifically interested about it, and there are various types of it, but 90% of it is type 1. Type 4, for instance, is in the basement membranes of your blood vessels and epithelial tissue. type 3 is in your skin. There's a variety of types of collagen, but type 1 is the one that has the majority of it and is present in almost all of these tissue sites, okay? So usually when we're making a tissue chip like the ones you saw last week, we line it with collagen, we cover it with collagen to allow for those cellular interactions, because it has all those cool domains that stick to the cells and enable vascular integration. Now, how does collagen look like? You may have seen this before, but if you put those sequences of amino acids next to each other, you'll get a molecular chain. Okay, this chain then turns into this helical chain, which has the geometrical configuration of that single helix, and then it coils around 3 other of these molecular chains, and so it becomes a triple helix. Like your DNA is a double helix, this one's a triple. And between these coils you have bondings, and the same sort of bondings that you have in the DNA, and they come together to form these microfibrils and fibrils that then assemble into larger collagen fibers. So if I, this image probably shows it better. There's a multiple, there's multiple levels of hierarchy, all the way from the main fiber down to the fibrils and microfibrils, and then the molecule, which is a triple helix, and that's the structure of it, which we just looked at. So what we do is we take this collagen, we denature it, meaning we take apart these 3 strands of the helix and we turn it into gelatin. Now the gelatin is much thinner, it's not as thick and fibrous and rigid or sturdy as collagen, so we can use it as a coating. It's a very smooth liquid that gels, and we actually have a much easier time working with it because it has a lot lower viscosity, and so we inject it in our vessels and chips, and that's how we initiate cellular adhesion. And another thing that we do is we actually mix it with water, and it encapsulates the water in it, providing a 3D environment for the cells to then be encapsulated and have the maneuverability to remodel. Previously, it was only done with heating, so thermal curing, thermal gelation, but now we're actually using light to do that. As I explained, this is sort of something that happened now 13 years ago when we first found a gelatin that's photocross-linkable, and since then that's been the main component of our tissue engineering and bioprinting systems, because light is the only way that we can have that much patterning flexibility. So, as I mentioned, you can encapsulate water in these structures, and what happens is some cases you utilize the inverse of that. So you, for instance, add the drug particles, you embed them in your matrix, and then when it goes in the body and comes into contact with water and swells, the drug gradually releases from those pores. So there are 2 aspects to it. One is producing a matrix that's good for cells and cell growth, but the other is to use it as the swelling happens to release stuff that is going to be useful in vivo. And it's very similar to those Orbis that you've seen. These materials are not that uncommon. You've definitely come across them, and the contact lenses that some of you may wear also are made out of hydrogels, not collagen but hydrogels in general, so they have water encapsulated and they can run dry. Now the problem with these materials is that they're very weak, okay? So what we do is we try and add mechanical integrity by making composites that incorporate these gels and a secondary component. And one of these cases is agarose. So agarose is the worst material ever because it doesn't promote cell adhesion and growth, but it has a very strong, sturdy shape to it. So it can take the shape of the mold that you cast it in, and it can retain that forever. Whereas collagen is this mushy thing that doesn't really retain its shape. So that's why the field of biocomposites was born, and the idea of mixing materials that have, the biology and the cell-friendly nature with materials that have the mechanics and the integrity to hold a geometry. And so combining these two together, you see a synergistic effect. So agarose alone as a very stiff material goes up to 7 kilopascals depending on how much powder or how much solid content you have in water. But if you add just 1% of agarose to collagen, you'll see that you you see that stark increase up to 12 kilopascals in collagen. So what happens is these two types of networks actually don't just linearly add up, but the synergistic cross-linking between these two and the force fields between the two molecular structures makes it even higher in terms of stiffness. And so what you do is you tune this value to your desired stiffness of that tissue that you're interested in to be able to mimic that environment. Now the problem is it's not just the stiffness. Stiffness influences cell growth through, as I mentioned, the cellular mobility. So here you're looking at cell growth in 3D. So these cells are mixed in the 3D volume and they're able to move around and form clusters. As you can see, the ones in high percentage, 1% agarose, and high is just 0.5% higher than the average, 1% or 0.75% more than the minimum. They turn out to be completely isolated. They cannot reach out to the other cells. A matter of just 0.5% of that content changes it entirely, so they form beautiful clusters. And their ability to now reach out their actin structures into that matrix is changed by that very tiny change in viscosity and stiffness. So you can see here they've been blocked. So here we've forced them into a cluster of cells, and then we've studied these as they grow into the matrix, and you can see that it changes tremendously when you reduce the stiffness. So we have to find the sweet spot. Okay, here we can't pattern, we cannot print a structure that's intact in 3D, and here we don't get biology. So we have to stick around there, although it's not ideal for biology. So, and when we talk about these gels, we want to mimic the various structures in our body. So a blood vessel, for instance, if it's a capillary, it only has endothelium. But when it's a multi-layered structure like the veins and arteries, then you're looking at different mechanical properties in each layer. So we have to be able to manipulate that mechanical behavior as every layer of this structure. And the structure alone is 100, 200 microns. The layers are just about 20 to 50 microns. So it's very difficult to pattern material properties at that fine of a resolution. But have in mind that, this is really where we excel in terms of tissue engineering, is our ability to figure out ways to manipulate mechanical properties of material and at the same time optimize biological performance. Okay, so now we're going to focus on this topic of mechanics and talk a little bit about this in the next couple of slides. So you're familiar with this concept of doing a linear tensile test, stretching stuff until they neck and then they at some point fail. Okay, so fracture in a typical polymer follows this curve. You have a linear region, then it becomes non-linear, it necks so it turns really thin, and that becomes even weaker until it fractures, okay? Now what happens in the case of our tissue is, as I've mentioned, even in this elastic region, it's not linear. What happens is this. So this is a little bit tricky to understand, but I'll try and sort of explain it in simple terms. So if you exert stress on a solid, what's going to happen if it's an elastic solid, it's going to deform to a certain level, and if it's within that elastic region and you let go, it's going to go back. So it goes to that constant strain and then drops off to zero if you let go. If it's in the plastic regime, it's not going to retain, it's not going to go back and recover its original length. It's going to go back to a plastic deformation state. So that's what you know about solids, okay, about plastics and regular polymers. Now, if you have a viscous material like a liquid, what happens? If you exert shear, what do you get? Do you get a constant strain? Huh? Uh-huh. Yes, so it depends on whether it's Newtonian or non-Newtonian, but again, still, do you get that constant deformation, or does it just go forever? Because it's a liquid, right? If you're exerting a force on it, it just goes forever. The strain is just going to grow. What's constant is the strain rate, the rate at which it starts flowing. is what's constant. It's not the amount of strain, because if you maintain the same force, it's just going to shear those layers of fluid and keep going. There's no barrier, okay? So, therefore, it has this sort of a ramp as you basically keep the constant stress on. It increases its strain until you let go and it stays at that strain level. It doesn't go back to zero. The fluid settles at that amount of displacement. Now, as you mentioned, if it's non-Newtonian, it can have this or that, so it can buckle upwards or downwards, showing that it's not a linear relationship with viscosity. If you put a huge amount of stress or less stress, you'll get a different response. So, but it's always going to be this region of increasing stress, because the increasing strain, because the strain rate is what depends on the stress. And now if you've got a viscoelastic material, it's got both of those. It's got a dynamic evolution of strain, okay, but it plateaus. It doesn't go forever because it's also a solid, right? And then if you let go, it's going to relax slowly into a resting state, okay, a non-zero resting state, because it's like honey, okay? When you have an impact, when you're stressing it, it doesn't respond immediately. It takes a while for it to respond, and it takes a while for it to rest, okay? So that's what the gist of viscoelasticity is, and that's really why in your skin you have the collagen and elastin doing two entirely different things. Elastin is an elastomer, it has an elastic behavior. That's why if you sort of do that to your skin and let go, it goes back to where it is, because of the elastins stretching it in the tension mode, and the collagens are pushing it in compression mode. So if you poke it, right, or if you actually try and basically force it into bending, it will go back. So collagens are in compression mode there, meaning that from elastins you expect an elastic behavior like a solid. From collagens you expect a viscoelastic behavior, because they are a protein that changes its solid or mechanical properties as you exert stress. And to understand these, we sort of model this, and I'm not going to go into the details of modeling this, but we model this with simple elements such as springs and dashpots, okay? Because a dashpot is a damper, it's the suspension you have on your car, right? And we model that with combinations of these to sort of get the equivalent behavior as what you have here. So, these are a couple of those models, and if you're doing tissue mechanics, this is definitely something you'll come across, okay? The Maxwell model, the Kelvin-Voigt model, or the linear model. And each of these models the behavior with either a parallel set, a series set, or a more complex set of springs and dashpots to get that same. So you basically use this input, you plug it into the behavior of that, the functional behavior of that, and then you get an output curve, and then you compare these two to see whether the performance is what you expect in the actual material, and then you fit those constants in. Okay? So clear so far? So now we're going to look at a functional use of these materials, and that's in a structure you've already seen. Okay, the alveoli, okay, this lining here is an elastic lining the epithelial cells produce. And as a matter of fact, epithelial cells are the cells in charge of secreting these matrix proteins and building their own ECM. So if you have, wounds and it starts to do the wound repair mechanism, the ultimate stage is where the epithelial cells start to secrete collagen and elastin and then induce that bridging that will then heal it fully. So the cells in this interface are going to produce this, and then you've got the endothelial layer here, which is really thin, so that one doesn't have any elastic matrices in its basement, it's just got an endothelium. Now the question is, with these elastic properties, how is it that these do not collapse, okay, when you breathe, okay? How is it that your alveoli sacs, these tiny bubble-like clusters, how is it that they maintain their shape and do not collapse as you breathe? Now you may wonder, why would they collapse at all? But if we look closer in the next couple of slides, that question will arise. So surface tension is something that you're well familiar with, okay? It doesn't just happen in insects, with very thin, small surface area. It happens in droplets and bubbles. And these two are a little bit different, but in their core they're the same. Droplets have entirely been filled with water, and then you've got air, so you've got one surface tension acting on the external surface. Droplets are a film of liquid. Inside and outside there's air, so you've got two sides that the surface tension is going to act on, both the internal interface with air and the external with air. So if we try and model this, and using really simple surface tension physics, what we're going to do is we're going to write an equilibrium between, this equilibrium is between the internal pressure and the external pressure, keeping this bubble in a steady state. So if we sort of cut this bubble in half and look at the top half of it, okay, and then you've got the tension, the surface tension exerted by the bottom half on that line around it, and you've got the pressure inside this bubble forcing it to the outside and the pressure outside forcing inwards. So there's a difference between those two pressures, which is acting on an area, that projection area, that circle, and then you've got the tension, which is only acting on a line, which is that periphery. So that's why this is 2 pi times r. That one is pi r squared, because the pressure is acting on a surface, but surface tension is actually acting on that line of interface, whether it's just on the outside of the droplet, or in this case there's one on the outside line and one in the inside line, with the air in the inside and outside. So if we put those two in balance, you'll simply see that for a bubble, the difference of pressure is 4 times that surface tension value divided by r. For a droplet, it's actually half of that, twice the surface tension divided by r, because you only have that outer ring which is interfacing with air. So now this is where I'm going to ask you to tell me why your alveoli don't collapse. Naturally, if we have a small sac and a large sac, the small sac should have a higher pressure. If we have a constant surface tension running through this entire system, because it's all stable and it's all connected, so there should be a balance. So with that same surface tension, you expect the smaller sac to actually have higher pressure, meaning that it will squeeze flow to the larger sac, and therefore it will collapse. And as it collapses, the radius gets smaller and smaller, and so the pressure will get even higher, and so it will just be more fond of this pushing the flow, or the cross flow, from the smaller to the larger. And this is what happens when you have a cluster of bubbles. They all coagulate, they all become one large bubble, going from the smaller bubble, collapsing into the larger ones, and it can't stay stable. Now, the same story is in your alveoli. Why is it that the smaller ones do not collapse, and then gradually the larger one then collapses to an even larger one, and so on and so forth? Okay? Why don't we have this cross flow causing complete failure? Any idea?
Open and close at the same time.
So when you're inhaling, they all open. When you're exhaling, they close. But the thing is, when you're exhaling, okay, it's not always the deep breaths that you take air in. Sometimes it's all just disconnected from here, and they have a chance to now connect with each other, right? Because you're closing the tracheal input, right? What I'm saying is, in that phase, why don't the larger ones all take over, right? And even in that transitional phase, it's very much possible that, you've got a long period of time, you don't take deep breaths every so often, so there is a chance for these two to meet and have cross flow. So what's the reason that this doesn't collapse? So the oxygen here diffuses through to the blood vessels, but the air coming in, actually, a very small amount of it is, and also it comes with such high pressure that in that intake you don't absorb the entire gas through your blood vessels, it's just a small portion of it. So no, it's not that. Think of soap bubbles. Why do they stay stable? Yep.
So is there always a level of air in the lungs or in our lungs?
There is a dead level of air, but in that state, so let's say you don't breathe for a while and there's dead air in there, why should it not go from one to the other? Because just knowing that your sacs are not the same size, the smaller alveoli and larger ones, you should expect that they all collapse into one huge alveoli, right? So what I'm saying is that even in that case, although you have a resting volume, you still should see this. But what's in the soap bubble thing that we haven't looked at here? Lipid? Yes, there's a surfactant there. Exactly. So it's oil or lipid. There's a surfactant, and that surfactant is what reduces the load between those molecules, causing the surface tension. So if I sort of look at this, the same thing that happens in bubbles and everything starts to collapse very fast, it doesn't happen in your lungs. Now, before we get to that, okay, just giving you a simple example of how this all happens. So the question I'm asking you is, knowing this simple formula for a single bubble, okay, what is that radius of curvature of this inside wall, the interface of these two bubbles? Okay, so you know one is R1, the other is R2. Okay, the question is, and there's an external pressure here, what's that radius of that internal one? Is it similar to the small radius, the larger one, or is it somewhere in between? What's the value associated with that? Simple to figure out. Just write this down. And note that the tension is the same in all of these liquid layers, because this happens to be 120 degrees in each side. So there's an equilibrium in this junction. So the tension is all going to be the same. So if you use that, could someone tell me what the radius R3 is? And then we'll get back to surfactants. You guys just all do it in your minds, right? Not on paper. That's good. So what is it? It's just 2 lines of derivation. It's not that much. Okay, I'll leave that as a practice for you guys, and I won't reveal that, okay? But we'll talk about that in class maybe. We'll have a few minutes in the lab session that we'll sort of do that, but just good practice to see how bubbles conglomerate. And then I'll send you a paper which is actually interesting. They're using these bubbles to produce structures that do mimic the lung alveoli. So imagine if you could have that liquid that encapsulates the bubbles be a polymer, and you would shine light and cross-link it while it's in the bubble state. You would basically solidify that bubble structure, which is the alveoli sac. So that's an idea in producing functional lungs. But the problem is, these bubbles are not connected. So as you inject air in one, it doesn't just spread across all. So that's a big challenge. But anyway, so we were talking about surfactants. This is the cross flow. And why don't we have that? It's because these surfactant molecules, okay, what they do is they repel these other molecules that have the surface tension, and they reduce the surface tension by disrupting those interactions. And so what happens is that they, reducing the surface tension and doing this non-linearly, depending on the radius, they influence these two sacs in a different way. And it's the exact physics of those that changes the story. Originally, this would have always had, if this radius was twice smaller than that one, or half that, then you would have had a pressure twice of the larger one. In this case, you actually end up having the same pressure because your surface tension ends up also being different for these two, so it compensates for the effective radius. So that's why you see a balance of pressure and you never get that cross flow happening between these. And what's interesting is that actually when it comes to smokers, this surfactant is secreted by the epithelial cells, okay? And so this, the alveolar cells are actually what type 2s are what secrete these surfactants, and if they become dysfunctional, they don't produce the surfactant, the lung can collapse in every cycle, or at least not retain its original shape and therefore cannot breathe normally. It's just because of that absence of that surfactant and the improper expansion and collapse of these alveoli sacs. So it's all about being able to eliminate cross-flow and having the natural breathing where everything gets inflated at the same time and then deflated. That's the natural way it should work. And if you don't have that, if you don't have the surfactants, there's going to be cross-flow, and that's what's really going to cause trouble. Okay, so I'll leave that tiny derivation for you guys, but now let's just talk a little bit about the lab session ahead of us. So you guys have printed this very simple but very nice experimental chip that has a source, a drain and a channel. What you'll be doing in the lab is you'll be given the chips that you've made, and then you'll be able to use that fixture to fill those two inlet and outlet chambers and then inject the gel into that central chamber or that channel. And then once you do that, you're going to put them all back in the petri dish, give those to us, we'll put them in the fridge and they'll set into a gel. And then what we're going to do is half an hour later, and in this meantime you've had time to do the mass measurements and calculate the conversion of your cubes, you'll be able to now continue working on these after like 40 minutes, 50 minutes into the lab. And then what you'll do is you'll input a droplet of ink, food colouring in one of those chambers and look at it as it travels through that channel. Now, you may or may not see a significant progression, but you're going to record that at the beginning, 30 minutes and 1 hour later, and then you will be able to use that data to do some calculations. Now, what's the calculation going to be? Well, when you have a source and you have diffusion going on, you usually have a Gaussian distribution, a normal distribution of that ink as it diffuses through the volume. Okay, and this is the equation governing that, and that's the diffusivity coefficient, and this is time. So as time passes, this curve is going to gradually bleed in, and your material is going to get transported through diffusion into the other side, the drainage. Okay, and what you can do, theoretically, if you're really enthusiastic, you can use this data, put it in MATLAB, and I'll share this piece of code with you, to find exactly what the pixel value, the colour, drops as it's running through the channel. And you can actually take the chips with you if you want and track it even after 1 hour, but we can't do it in the lab. And just take images of that and see basically as material diffuses through, you'll see this colour variation, and as it grows, you'll be able to sort of transform that into this Gaussian function. It should be Gaussian, hopefully, once you do it experimentally. And then from that, you can derive, if you have the time points, you can easily derive your diffusivity, knowing the other parameters, which you will also know because you've got the dimensions. So it's really an easy way to know what the diffusivity is, and what we're interested in is to compare the 4% and 8% gelatins, because the denser gelatin, finer cross-linking meshes, is supposed to have lower diffusivity, and I don't know if that really is going to be noticeable in your data, but it probably should be. So you'll probably see a different pace of diffusing through that channel in between. So really, this was a simple experiment, but it shows how much you can do. I mean, this channel could be made much smaller, and the multiplexing of that could bring to you hundreds and thousands of those channels on the same platform to do high throughput experiment. But the idea is that you see the potential and capacity of 3D printing to do a biological assay. We'll see more of this hopefully later. We're trying to design a level 7 module, which I think may be too late for you guys, but hopefully, I mean, you have the chance to participate in the third year projects if you're interested, and also it may kick in if you do a fourth year. This may be one of the modules that you will have there, which will be completely hands-on 3D printing based, and in that module you will actually get to design a device which you will actually see it travel through its, steps of development and become a tool that is used by maybe we'll have a fellow colleague in Barts or someone testing. It could be a surgical tool, it could be a fluidic screening tool or whatnot. But having this background really helps you to then utilize that potential. It could be a microfluidic chip or an implant or a surgical assist device. But we're working on that right now. Hopefully gets ready in time for the year after. But in any case, as I mentioned, the quiz will be the same time next week, 12 to 1. I've already announced the details there, but the link will be under the assessment tab, just like quiz 1. We won't have a class, therefore, next week this time, but I'll see you all in the lab on Tuesday. Okay? I hope you've had a good semester so far, and hopefully the content balance and the load hasn't been too frustrating, but we've tried to equalise it and improve next year. This was the first instance, so thank you for being so patient and such a good audience, okay? Thank you very much. Okay. Thanks a lot. Thank you. Thank you. Thank you.
I have a couple of questions about the final because I'm taking like what's the format? Like I'm taking it also like I'm gonna take them the lab quiz and the final.
Yeah, no.
On the same day, but it's okay. I'm wondering like what's the format? Like what's gonna be focused on? Like,
Yeah, the final has about 25 questions of the stuff that I covered and about 20 from Karen's stuff. So it's about 40, 50 multiple choice questions.
Okay.
And I believe we've given you, I don't know, 2 to 3 minutes something, but we'll announce the exact time of it. I think it's a 2-hour evaluation. But yeah, we'll tell you exactly what that is. And then it's just going to be similar to the EMS519 that you guys have taken, so multiple choice. We have negative points if there is an incorrect answer, and therefore you can't just mark everything. That's the idea really. But it's not all or nothing like we've had before. If you have a partial correct choice, you'll get the grade for that. If you've got an incorrect choice, that will have a negative point.
Okay, so it's gonna be. So I should focus like on everything, like dental materials.
It will be everything apart from a little bit the lab stuff too, a little bit of the lab stuff, not much, but just the main concept you take away. With you.
I mean, I'm gonna just need to study for the lab because I have to have the same day. So like,
so it'll help you. That will give you 1 or 2 more questions that you can answer easily.
Okay,
for that stuff. But yeah, the idea is that you really.
Okay, so about like 50 multiple choice questions about with like everything.
Yeah.
All right.
But don't worry, it's not that tricky. You all do very well as long as you really.
Hopefully.
Yeah.
Thank you so much.
Yeah, you're welcome too.
With the lab, I was just checking because I was in the first group in the first lab, and some of our components for the chips, the gel ones.
No worries, we've made sure that each of you have so we've made a couple more and we've added to those that didn't have enough of those.
Yeah, because we didn't have one of the, I think, the ones with the holes.
That's fine, we've made more and you'll have at least 2 of those for every experiment, so 4 overall for every, so they'll be fine. Don't worry. That was our problem, the printers weren't functioning properly, and so
Although
hopefully you got the experience, but the rest of it is fine. Okay, wonderful.
Thank you.
Okay, sure.
I'm just here to wish you a Merry Christmas. Just
Oh, thank you so much. Thanks a
thank
lot.
you
Yeah, I
for
like
the,
these coins a lot. Thank you so much. Thank you. Very much appreciated. Thanks. Hey guys,
Just going to ask, what percentage of the final exam is on your stuff and what percentage is on Karen's stuff?
So about 25 questions from my stuff and about 22 on Karen to be precise. So it's about 50 overall. A little bit more than half. I think you get about 2 hours, but we'll tell you the exact specific. There's plenty of time. Don't worry. There's lots of questions.
So multiple choice question.
Multiple choice. Yeah, it's not all or nothing. So you get partial credit if you answer something.
Final exam you asked
Yeah,
for?
fine.
Yeah, the final. Yeah. So, but I'm sure that you all do.
And the quiz coming on Thursday is based on
Lab stuff.
labs only.
Only the 2 labs that I've had. So it's just the 3D printing stuff, the diffusion, and post-processing, stuff like that, conversion, yeah.
Perfect.
Okay, sure, you're very welcome. Yeah.
I emailed you like last week.
Oh,
But
okay.
I think you might have thought I was the first year.
I did,
yeah.
yes, that was you.
But then I came
No.
on Monday to see, to clarify, but you weren't there.
Yeah.
So I'm like, is it still okay if I
Absolutely, yeah. Sorry, so the situation is I found a few of you that are really enthusiastic about 3D printing and stuff. It's just that I've had this 2 grant deadlines this past week, and then this other module 430, which you guys took before, has 5 classes every week and stuff, so it's divided and so it's been super busy. But what I'm planning to do is through the Christmas break, hopefully before it, I'll send you an email to all of you, the cohort who are interested in doing this stuff, with a couple of papers which you can do some study, and then we'll gather all together after the Christmas break and see what the best way is to integrate you within the lab activities and get you involved and then get you ready for a 3rd-year project. So hopefully that's the plan too.
That sounds good.
So we'll give more structure to everything.
Amazing, okay.
But don't worry, I have my
I just
eyes
thought
on that.
maybe you didn't see my email or something, so I was like, let me just check.
No, I know. No, absolutely, that's
Perfect,
fine.
that's
Yeah, I'll
fine.
get back to you all very
Perfect.
soon.
Thank you so
Thank you. Take care. Take care. See you.
So cold now. Wearing like 5 layers of clothes. You know, I'm still thinking about micro.
I forgot.
I'm still thinking about like I'm going to the electronics lab now or something.
You know what? Well,
It's a habit.
I know I don't want to see the electronic stuff for I literally woke up this morning. Yeah.
Did you finish the calculator by the way?
Sorry?
Did you finish the calculator?
No. But I wrote a plan.
Yeah, that'll get you like half.
Yeah.
And it's only 6 marks, so it's not that bad. Yeah. All of that was 6 marks.
Well, to be fair, it helps you with the other parts.
So the multiplex displays 11. The first part A is 11 marks.
Yeah.
Then the calculator.
Internal part 6 to 1.
4.
No, it's 11.
11, 6,
It's
and 4.
out of 23%.
So on one each particle of I wrote?
Most likely.
So it's 22%.
Because I wrote for the first thing before I asked you, I had 1 line for that.
Oh yeah, then I
I
added.
said added delay, delay was something.
I added degree milliseconds, but the person will press this.
I started making up stuff and then
Bro,
I said,
the flicker question. I just illusion of continuity.
yeah, I said delay
No, I
too.
basically said, in the case of no key press, it's I changed basically my delay from 7 to 5.
Yeah.
So like the hex value. So basically it's less than the refresh rate.
Yeah.
So it's still fine. Well, of course, when there's a key press, there's a slight sense of flicker, but it's unnoticeable. So I just said that.
So it's 11 part A, 6 part B, 4 part C, and 3 from the MySQL.
I didn't do the mic.
My school
My-
is 18.
Bro,
I
MySQL.
said when I'm done with that.
Do you guys have extracurricular activities?
No.
I don't have.
You don't have to.
No, they have to enter 3.
It says-
That's the thing.
Or just make up stuff.
Oh, I work.
Yeah, I'm gonna say تعرف لوياك اللي بالكويت؟ ايه I'm gonna say I worked for لوياك in the summer بالكويت حاول
لا to be fair ما أعرف اللويا لأن في فرص أظن مع الصناعات الغانم. شنو بعد؟
أنا صاحبي دش فارمز شغال فارمز
بس ما أعرف لأن ما يقولون ترى الفرص. ترى عمار قال لي في ويب سايت بالكويت فرص عمل like internships and you basically just like apply.
Nice.
عمار؟
إيه.
لا هو كان داش ماركتينج بالسما كذا ماركتينج ايفنتس وما ادري شنو
أنا شكلي راح أدش مشروع مع أخوي or
I'm trying to find an internship here.
I'm gonna go back home. Because like,
There's no such thing as relax, خلاص.
I already have like an idea what to do. I'm gonna do this course. I'm gonna do this business. I did like
I'm gonna start e-commerce.
I literally created like a business idea.
2 years ago I started dropshipping and I was 3 just kidding. I'm not doing it again.
Then you're
Well,
then for me, I did the startup costs and I saved up the money. It's basically
what's your business? E-com يعني online
no,
business?
basically like yeah. So what I can do, and this is the way like I did my research. If you set up a US LLC, you don't pay US taxes if it's outside of the US. Okay.
The business is in Kuwait or
But
UK?
Where are you based?
Okay, here's the thing.
You're not
Okay.
based anywhere.
No, I'll tell you why.
Uh-huh.
Okay, because if you set up abroad and you sell products to the GCC in terms of e-commerce sales per capita is about $120. That's about 3 times the rest of the world. Okay.
Uh-huh.
So what I can do, I already have done my research with distributors in Italy, and they can
Bros, worldwide market.
distributors with Italy.
Is the teacher not coming in?
And
Yes, she's
she
coming.
is, but she's gonna be a bit
Yeah.
late. But and they're already
Amazon.
بس شوف لأن المشكلة شنو راح يصير
نعم.
مع الوكالات. So basically certain
What are you selling?
I'll tell you what, it's nice. There's certain people in Kuwait that have the sole license to sell the product.
Yeah.
But what I can do, if by using a US Delaware LLC, They're not able to know my identity and they can skirt around the rules.
But what are you selling? What's the concept?
No, my name is only share.
No, but my question.
If I'm incorporated elsewhere, they can't.
No, but my question is. Yes, it's
So
what.
basically, I looked at the distributors and I looked at their products. I'm still doing some research, but they basically have perfume.
Oh.
They basically connect you with like product, sellers like Gucci, A, and Khan, and they can. All you need to do is basically just send an order to them, and then you use necessarily like apps to adoption.
Yeah, he's just like going around the practicing.
Well, yeah, you don't need to pay.
Yeah, no. The thing is, there's a high chance of failure. Oh, you guys don't. You don't like. Yeah, I understand.
So like, if I put like maybe something, and I can get. I don't need